Okay, this is going to be a little introduction video to the new series of tests that I've done. I've done a whole bunch of coupled oscillator tests once again, and this time with the main focus to make sure that both pendulums would come to a full stop, right? To make sure that they would transfer all of their energy from the one mass into the two mass and from two mass into the one mass. It turns out that is really difficult. I've tried to change a lot of things in the setup, trying to change the positions of the pendulums on the steel bar, trying to change the position of the connecting string higher and lower, changing different weights in the middle of the connecting string. But unfortunately, both pendulums would never come to a full stop. What would happen is I would always deal with three possible scenarios or cases. In one case, the one mass would come to a full stop and two mass would still swing a little bit and thereby not having transferred all of its energy. And that was the main complaint in the previous experiment. In another case, we have the one mass still swinging a little bit and the two mass coming to a full stop, right? And therefore, yeah, the one mass not giving all of its energy to the two mass, but vice versa, the two mass would give all of its energy to the one mass because the two mass would come to a full stop, right? And then we have the third case where the one mass would still swing a little bit and two mass would still swing a little bit. And that seems to be the most equal case, the most fair scenario, right? So we have, again, three cases. In the one case, the one mass would come to a full stop and the two mass would still swing a little bit, right? But that would mean that the one mass would not transfer, that the two mass would not transfer all of its energy to the one mass, and that would not give us the right results. That would be in benefit for kinetic energy because the ratio between them would become smaller. It would become more, 1.4 or even less than 1.4. I have one case where it's actually 1.34, right? In the case where one mass comes to a full stop and the two mass still swings a little bit. In the other case, all right, so what I'm going to show you is the case, the two cases, right? The case where the one mass still swings a little bit and the two mass comes to a full stop, right? That would show you that the two mass has transferred all of its energy to the one mass because the two mass comes to a full stop. And then the ratio becomes bigger, right? The biggest ratio that I have that happened or occurred was 1.52 instead of 1.45, right? So 1.52. But only, if the two mass stay stationary and the one mass still swings a little bit. But that's also not going to be a fair result because the one mass did not give all of its energy to the two mass. So I believe that for my setup, right, in this case, the most fair case is the third case, or I believe I call it the third case. Case 3, one mass and two mass keep swinging a little bit. So in the third case, the one mass still swings a little bit and the two mass swings a little bit. They don't both come to a full stop. They still swing a little bit, all right? And I hope they swing the same amount. So in this case, they actually did kind of give the same. They did kind of transfer the same amount of energy. So let me already tell you, I'm going to show you the results. So this is in the first case, well, this is the case 3 where the one mass and the two mass keep swinging a little bit. Example 1. So case 3, example 1, the results are 1.4, 1.42, 1.41, 1.42. And then we have case 2, the one mass keeps swinging a little bit, and 2 mass comes to a full stop. Well, in this one, it's also 1.44 and 1.43. So this is the first example of case 2. I have 3 examples of each. And then we have case 3, example 2. So again, the one mass and the 2 mass keep swinging a little bit. We have ratios of 1.45, 1.46, and 1.46. And then we have case 3, example 3. So the one mass and the 2 mass keep swinging a little bit. Once again, same results, ratios of 1.44, 1.44, 1.44, and 1.45. And then case 2, example 2. So again, the one mass keeps swinging a little bit and the 2 mass comes to a full stop. 2 mass has transferred all the energy to the one mass. And here we have ratios of 1.51, 1.52, and 1.52. And then case 2, example 3. So another example of this case. Yeah, we have ratios of 1.46, 1.48, and 1.51. And then another one, yeah, I have 4 examples. We have ratios of 1.44, 1.50, and 1.51. So actually this case, right, where the 2 mass is stationary and the 1 mass still swings a little bit, this is in benefit of draft science model, because that would create a bigger ratio. But even then, it still only produces a ratio of 1.5, 1.52 at best. While theoretically, it should be a lot more closer to the number 2 for draft science model. That clearly does not happen. It's still at the beginning of 1.5, a lot more closer to 1.4. So, okay.